Hello, everyone. My name is Justin Maresco, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on NEHRP Seismic Design Technical Brief number 12, Seismic Design of Cold Form Steel Lateral Load Resisting Systems, a guide for practicing engineers. This webinar is part of the Applied Technology Council's webinar program, and it is made possible with the ATC Endowment Fund. The purpose of the ATC Endowment Fund is to support efforts of critical importance to structural engineering design practice, research, and education. More information about the ATC Endowment Fund can be found on the ATC website. So if you haven't already, you can download the handouts from the Handouts pod on the GoToWebinar control panel. We know that many of you are interested in receiving professional development hours for your participation today. Importantly, if you haven't already, registrants who would like a PDH certificate must pay $25 through the ATC online store by today and must attend the full duration of the webinar. ATC is charging this nominal fee in order to cover some of the costs of hosting this webinar. A link to the ATC online store will be provided to all registrants in an email distributed immediately following the webinar. For those who have already paid the fee and who attend the entire webinar, a certificate documenting PDH hours will be sent by email within 2 weeks. If at any time during the webinar you have questions, please type them in the questions pod in the GoToWebinar control panel. We're planning to have 3 live question and answer sessions during the webinar. The last question and answer session will be the longest, and we'll attempt to answer all submitted technical questions. If there are any that, due to time constraints, we're not able to answer live, we'll provide written responses to them after the webinar. So now that we've gotten through the housekeeping items, we wanted to start with a quick poll to better understand your familiarity with the topic today. So a window with the poll question should pop up shortly, and please respond quickly because we're only going to keep it open for a short amount of time. So hopefully everyone can see the poll now. Thanks to all of you who have voted. We're getting close. I'm going to hold it up just for a few more seconds. Getting close to 100% response. Okay. I'm going to close it now. And hopefully you can all see the results. So about 11 of you said that you don't have any experience or knowledge about seismic design of cold form steel lateral load resisting systems. 48% of you said limited, 33% of you said moderate, and 8% of you out there said extensive. So the nice thing is I think you're going to find that we will be providing relevant information in this webinar for all of you out there, regardless of your experience level. So let me tell you about your presenter today. His name is Rob Madsen, Associate Principal with Devco Engineering, Inc. in Enterprise, Oregon, where he specializes in the design of cold form steel framing. He serves on the AISI Committee on Specifications and the Committee on Framing Standards, and he currently chairs the Lateral Subcommittee. In 2016, he served as the chair of the Technical Review Committee of the Cold Form Steel Engineers Institute and received that organization's Distinguished Service Award in 2014. Rob was one of the 3 authors of Technical Brief number 12, which is the topic of today. I'd now like to turn the webinar over to Rob. Rob, please go ahead.
All right, thanks, Justin. And thanks everybody for joining in today. I see there's a lot of folks, and it sounds like we've got a wide variety of experience levels here. So hopefully we will be able to present information that is relevant and interesting to everybody. So today I'm going to provide a brief introduction to CFS and CFS lateral force resisting systems. We'll talk a little bit about the history of CFS. I will outline the available CFS design standards And a good portion of the discussion today is going to be about analysis and design of CFS seismic force resisting systems, which is the main topic of TB12. And we'll cover a handful of other topics that might be of interest to engineers and others. And as we go along, of course, as Justin said, we'll have a few opportunities for question and answer sessions. So jumping in, the design of CFS members and connections is sometimes considered a little more challenging than other materials, but I think the important thing to remember is that basic mechanics still apply. So all of the procedures that structural engineers are accustomed to using can still be used to analyze a CFS structure. Complexities arise though in predicting member strength. In particular, complexities include local buckling, which is a buckling of a flange or a web or a stiffener plate between or beyond the corners of the shape. There's distortional buckling, which is a buckling mode where the section distorts, so the corners move relative to each other. And cold form steel lends itself to open cross sections such as C shapes, and the shear center of a C shape falls outside the section. And so the application of load along a flange, for example, you can see in the diagram at the right, can cause torsional stresses if the section is unrestrained. So common CFS construction types include traditional bearing wall structures with floor joists and roof joists or trusses just resting on load-bearing studs. Podium type structures where a CFS load-bearing structure is actually built on top of a lower level podium of some other construction such as concrete or hot rolled steel. You see this sometimes, for example, with maybe a hotel or residential type structure sitting on top of a parking structure. There are also structures with CFS gravity systems that leverage lateral systems of other materials such as concrete or CMU shear walls, maybe like an elevator or stair core. And it could also be structural steel brace frames or moment frames. And penthouse structures on the top of taller maybe concrete or steel buildings are also common, but those are generally designed for a different set of loading and criteria, since they are typically considered elements and components rather than part of the main building structure. So shear walls are one of the most common CFS seismic force resisting systems. We'll talk quite a bit more about shear walls when we get into the analysis and design part of the webinar. Strap brace walls are another common seismic force resisting system. With one nice feature of the strap braced walls is that they just offer a straightforward analysis and design. So just really simple mechanics to figure out the basic force transfers and so forth in a strap brace wall. And then there are also special bolted moment frames, which can be used for mezzanine and platform construction. We'll talk more about those later on also. And with regard to history, so cold form steel structures, particularly in seismic design, have come more mainstream in recent years, but the use of cold form steel for building construction has been around since at least the 1850s in both the US and England. During the California gold rush, CFS houses were advertised as being cheaper than wood and fireproof and could be built in a day. And in fact, the 1933 Chicago World's Fair featured a steel framed house called the Strand Steel House. So research into the structural behavior of cold form steel started around 1939. It's performed primarily by George Winter at Cornell University under the sponsorship of the American Iron and Steel Institute. Folks who have dug back into not just cold form steel, but a number of structural topics from the 1930s and 40s are probably very familiar with George Winter's name. He did an awful lot of work, but most of the early work on cold form steel was under his direction. So the work by Dr. Winter proved timely as World War II came to an end and the wartime sheet steel production was able to be converted into domestic use. And then based on all this early research in 1946, AISI published its first specification called the AISI Specification for the Design of Light Gauge Steel Structural Members. So that was, of course, the predecessor to what is now AISI S400, or what's sometimes called the NAS spec, or just this AISI spec. So in 1947, Dr. Winter published his work on the effective width method, which is essentially a method of predicting the portions of a section that remain effective after local buckling has occurred. So local buckling in a stud, for example, let's say local buckling the flange, doesn't mean that the member has failed. There are stress transfer mechanisms in the section that can provide for significant post-buckling strength. The method that Dr. Winter developed actually in its basic form is still used today for predicting the strength and stiffness of cold form steel members. 1950s and 60s saw the use of gypsum products grow, where gypsum board coupled with steel framing began to find acceptance in fire resistive construction. And then in the 1990s, we finally started to see some standardization occurring in the industry. Metal Stud Manufacturers Association, MSMA, was one of the first organizations to recognize the benefit of having standard shapes with common names that designers could specify and builders could buy without the need to pre-select a manufacturer. So anybody that was around in the early 90s or before may recall that if you were going to specify metal stud, you kind of had to pick one manufacturer and use their nomenclature and their shapes and their structural data. But starting in 1990, you could finally specify a shape and it could come from any number of manufacturers with some assurance that the section would be standardized and meet the specific requirements of your design. In 1994, the Light Gauge Steel Engineers Association, or LGSEA, was formed. That's now called CFSCI, or the Cold Form Steel Engineers Institute. And that was formed to disseminate technical information and provide design guidance to engineers. And in 1998, AISI formed the Committee on Framing Standards to develop standards for design and construction specifically related to the cold form steel framing industry. The development of CFS lateral systems has kind of been more recent. And while the material, steel, used in a CFS lateral system is similar to hot rolled construction, there are a lot of significant differences between the design, particularly as they relate to connections. In fact, CFS construction in large part, methods and connection types are more like those you might find in wood framing, including the use of repetitive framing. So you got framing members at relatively tight spacings, like 16 or 24 inches on center. So some of the first research into CFS shear walls was completed by Dr. Renaud Surette at the University of Santa Clara about 1997. Those shear wall strengths were adopted actually in the 1997 UBC, or the Uniform Building Code, which was the predecessor to the International Building Code, IBC. And in 2004, AISI published the standard for cold form steel framing lateral design. That standard included provisions for wood structural panel shear walls, steel sheet shear walls, and also diaphragms. So research on these systems has continued and the standards have continued to evolve as we've learned more. And in 2007, AISI published AISI S400-20, which expanded on the 2004 lateral standard. And then in 2015, the seismic provisions of AISI S400 and AIS 110, which was the special bolted moment frame standard, were combined into a single dedicated seismic standard, which was AISI S400-15. So since that time, S400 has been updated, first with a supplement S116 and then to S400-20. And these updates reflect what we learned through additional research and input from users of the standard. AISI actually publishes most of the technical standards for the design of CFS members and systems. First and foremost is AISI S100, which is the North American specification for the design of cold form steel structural members. You may be familiar with this document as just the AISI spec or the NAS spec. In more recent times, people have kind of become accustomed to calling it S100. But S100 provides methods for predicting member strength, stability, and also includes provisions for the design of connections. AISI also publishes a number of standards to address industry issues specifically related to cold form steel framing. AISI S400-20 is a product standard. It addresses material and product requirements for both structural and non-structural members. S400-202 is the code of standard practice, which addresses design, fabrication, and installation of CFS structural framing. S400-30 is a prescriptive standard which provides requirements for the design of residential structures up to 3 stories in height. So generally this is not for use in determining engineering designs so much as for unengineered systems where a builder can use the standard without necessarily going through all of the engineering processes. S400-10 applies to horizontal and vertical diaphragms using profiled steel panels, and it provides the strength and the stiffness of the diaphragm membrane. It doesn't provide design of the full diaphragm system, so keep that in mind if you're turning to S400-10. All the information you would need to look at the diaphragm membrane and its connection to the structural members is in there, including strength and stiffness provisions, but it won't tell you, for example, how to design a collector, or chord forces and those sorts of things. So those you would refer back to, say, an S400 or an S400 for additional guidance. And test standards for a variety of members and assemblies are provided in the S900 series standards. And these and other standards are available for free download at cfsei.org. I would like to note actually that the printed version of this presentation had an error in that. It was based on where they used to be available. So if you've got your printed version handy, you might cross out the AISIstandards.org and write in cfsei.org. So AISI S400 is the North American standard for cold form steel structural framing, and that was just recently updated in 2020. That update, in fact, became available just a couple of weeks ago. So if you go to that cfsei.org and look for the free standards downloads, you can find the most current version of S400. And S400 consolidated a number of earlier design standards, including standards for the design of wall studs, floors and ceilings, headers, roof framing, and the wind and low seismic design of lateral systems. And when we say low seismic, what we're talking about is seismic design categories B or C with a seismic response modification factor R equals 3. Sometimes folks think that it should be R less than or equal to 3, and it's kind of a weird setup, but it is actually very specifically R equals 3, and there's a few reasons for that with regard to a very particular system in ASCE 7 that uses R equal 3. But for practical purposes, low seismic design category would be your C, R equals 3. If you're there, you can use S400. If not, you've got to go to S400. So the AISI standard most relevant to technical brief TB12 is S400, the North American standard for seismic design of cold form steel structural systems. TB12 happened to be based on S400-15 with the supplement number 1 or S400-15/S1-16. So S400-15 combined the high seismic provisions of S213 and the special bolted moment provisions of AISI S110. One of the goals in developing S400 was to provide clarity and uniformity in the design provisions for CFS seismic systems. Anybody that spent a lot of time digging through S213 might recall that while the provisions were all there, they were sometimes hard to find and not necessarily organized in a way that made it super conducive to understanding exactly what all requirements might be applicable to your particular system. S400 went a long ways towards streamlining that process so that it was just a lot easier to understand what the requirements were and to perform your designs. And that was largely accomplished by specifically defining the designated energy dissipating mechanism for each seismic force resisting system and providing a consistent design approach and language for each of the systems. So S400-20 is the second full edition of S400 and includes a number of clarifications and a few substantial technical updates. One of the things we did was we provided a better definition for capacity protected components, replaced that definition, replaced lists, what we called at AISI Lateral laundry lists of protected items. It was repeated over and over again in various provisions. So it's much easier to read now and understand what parts of your seismic force resisting system require capacity protection. The drift limitations for CFS buildings with concrete or masonry walls, those were updated now to directly reference ASCE 7. And S400 has always used what's called capacity-based design principles, but the specified value of the expected strength factor, omega E is what we use in S400 for shear walls. In earlier versions were such that overstrength always controlled. So when you were doing a seismic design, S400 would tell you that you could use the lesser of expected strength or forces from the applicable building code with overstrength, but it turned out that overstrength forces would always control. So S400-20 adopted a more realistic approach that determines expected strength based on the expected strength of the seismic force resisting system itself and additional strength that results from the attachment of finishes such as added layers of gypsum board, plaster, or EIFS. Steel deck diaphragm provisions were also added in Chapter F of S400-20, including methods that could be used where special seismic detailing is required by the applicable building code. ASTM also publishes a number of standards relevant to CFS design and installation. ASTM C645 and 754 are the product and installation standards related to non-structural CFS products. C955 and C1007 provide product and installation requirements for structural CFS products. And there are a number of sheet steel standards, in fact, volumes and volumes of sheet steel standards, but A1003 is geared specifically towards sheet steels used for CFS framing. And of course, no list of structural design standards can be complete without talking about ASCE 7. ASCE 7, of course, includes provisions for a variety of building materials and systems, where engineers look to ASCE 7 for seismic requirements such as the response modification factor, the overstrength factor omega naught, deflection amplification factor CD, as well as specific detailing requirements for a variety of structural systems. And ASCE 41 is specifically geared towards evaluation and retrofit of existing buildings, but it can be used for new buildings as well. And ASCE 4113, while it included some CFS provisions, there were a number of gaps. So it was difficult to actually use ASCE 4113 to do a seismic evaluation and retrofit of an existing building or design a new building based entirely on 4113. ASCE 4117 added significant content, including modeling acceptance criteria for CFS components. And NIST very recently published a technical note that did a comparison of the design of a building based on ASCE 4117 as a new building to the exact same building designed based on ASCE 710 and AISI S400-20 with supplement number 1. And it did find that there were a number of differences. I would encourage you to read that if you have interest in digging a little bit deeper, but it is a very interesting piece of work with regard to the differences between the approach used in ASCE 41 versus those used in ASCE 7 and S400. Anyway, the hope is that that study and follow-up studies will lead to additional improvements to ASCE 41, particularly as they pertain to new designs. And with that, we are to our first series of questions. So Justin, if you have any questions, you can.
Yeah, we do. All right, can you hear me, Rob?
I can.
Good. Okay, yeah, we've got a few good questions here. Okay, the first one, so how have CFS systems performed in past earthquakes? And sort of tied to that would be, how is their performance compared with wood-light frame shear wall systems?
So I must admit, I don't know that the CFS that there were a lot of load-bearing CFS systems that have gone through recent large seismic events. There are undoubtedly a few. I've seen very little data on how exactly they performed. In some regards, I would suggest that that might be a good thing, because if there were a lot of bad performance issues, of course, we would be hearing about them. I will talk a little bit more about the general performance of CFS light frame constructed systems during even large shaking at the very end of the presentation today, when we talk about CFS NIST, which was some testing that we did on a shake table of a small structure that was very informative with regard to how these things behave. And I would have to kind of default in the same regard to how they perform relative to wood. If you compare, for example, the nominal shear capacity and the hysteretic behavior of the two systems, they're fairly similar. So I would say that overall, if properly designed, both of them would behave fairly well. And yeah, and probably provide fairly comparable performance. The difference, of course, are the the selection between one or the other would generally boil down to the type of structure, whether or not you needed certain fire resistive characteristics of steel, for example, or building heights and so forth that might lend themselves to one structure versus the other, or of course like economics.
Okay, yeah, thanks for that, Rob. Yeah, and it sounds like what we're going to learn more about some of the research that's gone on later on in the presentation. So, okay, so another question here. For the construction types shown, one of them was CFS gravity with other seismic force resisting systems. And so the question is, what are some of the common seismic force resistant systems that are used with CFS?
Yeah, so I have seen a number of buildings that have used CMU shear walls at like elevator stair core areas. So, like long skinny buildings that may have a core in the middle and on each end, for example, where the load bearing structure might be CFS and the core material was CMU. I've also seen very similar buildings, but with concrete, cast in place concrete cores. And I have from time to time seen buildings where they may even be a hybrid, where, for example, the upper floors use CFS lateral force resisting system elements like a shear wall or a strap brace wall, but lower down in the building, they might be, say, a structural concentric braced frame or something like that.
Okay, and the last one for you here, to see if you can think of this off the top of your head, but if you could recommend a good textbook to learn about design of CFS.
The best textbook that I am aware of, and I just happen to have a copy sitting right here, and so I grabbed it. It's called Cold Forged Steel Design by Dr. Wee Win Yu. This book is not necessarily geared towards providing like standard details of construction and so forth. But if you want to understand the basis of the AISI standards and the behavior of cold formed steel under load, that's probably the best reference you're going to find. In terms of more like day-to-day engineering practical type stuff rather than a textbook, I would refer to CFSEI, which publishes a number of technical notes. And there's some really great technical notes on a wide variety of topics that hit kind of more standard, like I say, day-to-day engineering type problems.
Okay, I think that's all we have time for this question and answer session.
All right, very good. Thanks a lot. And we will keep moving. So analysis and design, and we're going to spend most of the rest of our time in the analysis and design portion of the webinar. This is kind of my area of expertise, and it is the main body of TB12 is based on the analysis and design portion. So here we go. So the basic process for design of a structure with the CFS lateral system is really no different than that of any other type of structure. So for example, your base and story shears are calculated in accordance with the applicable building code, typically ASCE 7, although like we mentioned, it could be ASCE 41 or some other code. A preliminary layout of your shear walls or frames would be completed. And then based on the calculated story shears and the layout of your seismic force resisting system, the forces in each wall or frame would be calculated just to ensure that the demand doesn't exceed the capacity of the selected frame or wall. Then we would check for story drift, compare that to the code limitations. And with the configuration finalized, the specific parts of each seismic force resisting system would be designed, including the capacity protected components like cord studs, hold downs, and connections, and then the system can be detailed. We'll talk a lot about what I mean by capacity protected components as we go through the webinar. And then diaphragms could be designed. And if necessary, based on the diaphragm rigidity, the seismic force resisting system forces could be reanalyzed in what could be an iterative process. So seismic forces are usually determined in accordance with AISI 7, where AISI 7 provides a number of factors such as the response modification factor R, the overstrength omega naught, and deflection amplification factor C sub D for a variety of systems, including a variety of cold form steel lateral systems. And AISI 7 also specifies height limitations for a variety of structural systems. There's also special requirements with regard to vertical and horizontal irregularities, and provisions for addressing inherent and accidental torsion in your system, particularly with rigid and semi-rigid diaphragms. And with ASCE 41, seismic demands are determined based on the selected performance objectives, which include seismic hazard level, or how much shaking you think your structure might experience, and the desired structural performance level. In other words, so under that seismic shaking, how do you want your structure to come out of that? And there's a variety of potential structural performance levels to choose from, everything from immediate occupancy to collapse prevention. So ASCE 41 is more performance-based design. But with the seismic forces determined from whichever code you're using, engineers can turn to AISI S400 for design of the lateral force resisting system. And AISI S400 adopts specific language and a system hierarchy which can help engineers organize the design process. So the lateral force resisting system, which is like the broader look at the entirety of the parts of the structure that are resisting wind and seismic forces, includes all of the parts, both vertical and horizontal in the seismic load paths. So it's going to include diaphragms, it's going to include the seismic force resisting system, and it's going to include the designated energy dissipating mechanism. And it's kind of in that order. So the LFRS is the big picture stuff. The SFRS is more concentrated stuff, specifically designed to resist the seismic forces, normally like shear wall or a strap braced wall. And within the SFRS, there's an energy dissipating mechanism. And each of those are defined in S400. So within that lateral force resisting system is the seismic force resisting system. Again, structurally, it's the system specifically designed to provide resistance to seismic forces. And common types of CFS seismic force resisting systems include shear walls, strap braced walls, and special bolted moment frames. So the concept of the designated energy dissipating mechanism is really important to understanding CFS systems and other systems as well. But in particular with the CFS systems, the designated energy dissipating mechanism, or sometimes it's called the fuse, is the part of the seismic force resisting system that we rely on to dissipate energy. So elements of the lateral force resisting system that deliver load to and from the energy dissipating mechanism are capacity protected to ensure that the load can get to the mechanism. So I want to talk briefly about the notion of a structural failure in these types of systems. So in a large seismic event, we very specifically design so that the energy dissipating mechanism is activated. So for example, if you are designing a strap braced wall, we intend in a large seismic event that strap's going to yield. So yielding of the strap in that situation is not a failure, right? That if you designed such a system and it goes through a serious seismic event and those straps yield, things have worked perfectly. So it means that all of the parts of the system did their job to deliver the forces to that strap where the energy could be effectively dissipated. Doesn't mean you might not have to replace a seismic force resisting system. Yielding still is a situation that isn't going to repair itself, but it means that things have done exactly what you intended them to do, and it's probably made the structure perform as intended. So shear walls are one of the most common CFS seismic force resisting systems, and they can use wood structural panels, like plywood or OSB. They can use steel sheet, and in AISI S400 there are a variety of sheet steel thicknesses that are presented that can be used in a steel sheet diaphragm. Gypsum wallboard or fiberboard panels can also be used. As you might imagine, these two types of systems have fairly limited capacity and so fairly limited application in seismic force resisting systems, but they are there, and there are times when they can be useful. And of course, there's a variety of proprietary products out there that can also be used. And if you're going to go use the proprietary products, of course, you're going to rely on manufacturers' data to tell you what the appropriate seismic parameters are and what the available strength of those products would be. So the nominal strength for wood structural panel, sheet steel, gypsum board, and fiberboard shear panels are tabulated in S400, and they're generally tabulated for a variety of panel types, like I said, and like you see on the screen there, 1536-1 or 7/16 OSB, for example. There's also a variety of framing thickness. You see that in the designation thickness column there, and fastener configurations. So, basically your edge fastener spacing. S400 also includes provisions for both type 1 and type 2 shear walls. The designated energy dissipating mechanism for shear walls is typically the panel fastener interface and the panel itself, whether wood panels or sheet steel. So in a wood structural panel shear wall, for example, the energy is going to be dissipated as that screw tilts back and forth as the panel moves relative to the flange of the stud. And so you're basically elongating the holes in both the wood and the steel. That creates a bunch of friction and so forth, which can dissipate energy. The panel itself can also dissipate energy as it's moving and the panel works against itself. And in steel sheets, kind of the same thing. The deformations around the screw shank in the sheet steel and the flange of the stud can dissipate energy, and yielding of the steel sheet panel can also be activated, which can further dissipate energy. So S400 requires that elements in the critical load path that are not part of the energy dissipating mechanism be capacity protected to ensure that the energy can be dissipated without failure elsewhere in the seismic load path. So examples of shear wall elements that would require capacity protection include cord studs, collectors, and any splices, hold downs, and anchorage. So when I was defining capacity protection, I mentioned that it included elements that are in the seismic load path, but that are not part of the energy dissipating mechanism. So you would not, for example, size the shear panel and its fastenings for overstrength or expected strength, because you want those to be the limiting factor. So you would design those for the base level shear forces that you determined in accordance with the applicable building code, and then you would protect all of these other elements, cord studs, collectors, hold downs, anchorage, to ensure that those do not fail prior to engaging the energy dissipating mechanism of your system. So capacity protected elements have to be designed for the lesser of the expected strength of the seismic force resisting system, or the code prescribed seismic forces, including overstrength. This is one of those unusual situations in the building code where you get to calculate two force levels and take the lower of the two. And if you think about it, there's some reasonable reasons for that, right? So the available or the expected strength of the system is what used to be called the maximum force the system can deliver. In other words, you're designing these capacity protected components for a force level that has been elevated sufficiently to ensure that even if your designated energy dissipating mechanism is a little stronger than you thought, you're still going to be able to deliver forces to it and dissipate energy. If, for example, you just happen to have a very strong system, there's an out for you in the use of overstrength, right? So overstrength just takes the code prescribed forces and multiplies them by a factor of 2 or 2.5, depending on the system. It's not always 2 or 2.5, but those are examples of omega knots, to ensure again that, okay, your shear wall, for example, is designed for a certain force level, but all the stuff that is required to get the force to that shear wall is designed for maybe twice that, just to ensure that those elements in the seismic load path don't fail prior to engaging that energy dissipation. So for shear walls in S400-15 with the supplement number 1 of 2016, the expected strength factor for shear walls, omega E, was set to 1.8, which basically caused all the designs to be controlled by overstrength. In other words, expected strength was in there, but it was kind of not really useful because it would always exceed the available strength, including omega naught, or rather the seismic forces, including omega naught. S400-20 provides improved estimates of omega E that include the expected strength of the seismic force resisting system itself. That's the 1.1 VN term that you see there. In addition to additional strength added by finishes, or the V finish term that you see there. And we also, of course, have to calculate shear wall deflections in order to check drift limits. And a reasonable estimate of shear wall stiffness can be found in S400. The S400 shear wall deflection equation includes a linear elastic term, which represents cantilever beam flexure, which is basically the shortening and lengthening of your cord studs. It includes a term for deformations due to sheathing shear, includes a term, an empirical nonlinear term that was based on tests, and a term to account for hold down displacements. And for most designs, what you'll find is that the deflections are dominated by the nonlinear term and the hold down displacements. So it is interesting. In ASCE 7, the concept of calculating drift is that you calculate an elastic drift and then you amplify it by C sub D, right? You may have noticed that in my discussion here, I mentioned that we had a nonlinear term in that equation. That was based on tests, but it is recognized now by AISI at our lateral subcommittee that we are including some nonlinear and inelastic terms in our deflection estimations, which creates two things. One is it's probably overestimating the real elastic level deformations, but it also makes design of these systems iterative when you have to rely on the rigidity of the shear wall to determine forces. So for example, in a rigid or semi-rigid shear wall situation. So what you end up finding is that the stiffness of the shear wall is dependent on the force in the shear wall. So you have to iterate around and around to zero in on a solution where everything is aligned with regard to forces and deformations. It is our hope and intent that in the next code cycle we can fix that and actually come up with a linear elastic deflection equation that can then be used to more easily design to and be more consistent with ASCE 7's notion of the deformation amplifications. So strap braced walls. Strap braced walls are also very common CFS seismic force resisting system. And the nominal strength of strap braced walls can be determined by simple mechanics, although S400 does include equations for it. So, you can set up a little model or you can even do just basic statics for it. If you would rather, you can also just plug and chug with equations in S400. The designated energy dissipating mechanism of a strap braced wall is yielding of the tension straps. And the expected strength in S400-15 with the 16 supplement was based purely on the strap's nominal yield strength multiplied by a factor RY to account for statistical variation in the yield strength of the steel. And those values of RY were published in S400. They still are published in S400, of course. Now in S400-20, the V-finish term that we introduced for shear walls is also included for strap brace walls, which results in higher values of expected strength. So the expected strength in S400-20 is the old expected strength plus a little bit for added finishes. So to ensure that the yielding of the strap can occur, in other words, that we can activate the designated energy dissipating mechanism, it's critical that net section rupture of the strap is prevented. Net section rupture is where the strap at the connection fails brittly for practical purposes. In other words, it's not allowed to yield. The connection just kind of comes apart. So there's two methods that we can use in S400 to ensure that that doesn't happen. Method one is to just use welded connections configured to ensure that yielding of the gross cross section of the strap can occur. And method two is to ensure that the net section rupture strength exceeds the strap expected yield strength by meeting both of the requirements listed. One of the ways of meeting method two is to use like a tapered or dog bone type straps with a narrowed zone for yielding. So if you're familiar with moment frame design and structural steel, it's a little bit like that. In other words, that you're trying to direct the yielding mechanism to a very specific location within your seismic force resisting system so that you can control that and keep it away from columns in the case of moment frames, or strap connections in the case of a strap braced wall. It is also interesting to note that of the method two, there's the 2 bullet points. That first one, for certain types of straps, you just can't meet that. I believe it's a 33 KSI strap. I'm going from memory with that, but I believe a standard ASTM A653 33 KSI strap will always fail the first test. So you would either, in that instance, you would either need to use a welded connection, or you would need to change your straps to like a 50 KSI strap where the RT and FU and RY and FY values could meet the greater than or equal to 1.2 requirement there. So narrow strap braced walls, which are defined in S400 as having a height to width ratio greater than 1.9, present some unique problems due to the frame action caused by joint rigidity. And you can see in that picture on the right what I'm talking about. So that's a strap braced wall, which in its simplest sense you would think was pin-ended with tension in the straps and compression and tension in the cords. But that is not how they behave by the time you get all the straps and gusset plates and so forth in there. So S400 requires a frame analysis, including joint fixity at the corners for the design of those cord studs. And a frame model can be used, or the S400 commentary actually provides equations that you can use just to estimate the cord weak axis moments. And the model should include the tension straps, of course, as well as rigid corners in all 4 of the corner locations. And the model is used to determine the weak axis bending with MY for the cord design to ensure that premature cord failure doesn't happen. But the frame model should not be used to increase the nominal strength of the system, because we're estimating the rigidity of those connections, and they're normally not specifically designed for that. So while the rigidity is there, we don't want to rely on that to add strength to the system beyond what we would predict if it were not there. The model should also not be used to reduce the deflections. In other words, you would base your deflection calculations on a non-rigid frame model or a pinned end model, even though we have to design the cord studs for this notion of the rigid corners. So elements requiring capacity protection for a strap-based wall are really pretty much the same as those for the shear wall, including cords, collectors and their splices, hold downs, anchorage, but then also we have strap connections, right? So the strap connections are also capacity protection. And S400 also includes a series of special requirements for anchorage of strap brace walls. For example, uplift cannot be resisted by bending of a track web. In other words, you got to use a hold down. You can't just put an anchor next to your cord stud and call it good. Base track splices and shear anchors need to be designed for the horizontal component of the expected strength of the strap or the horizontal forces with overstrength. You can kind of imagine, for example, in a shear wall, the base shear is distributed along the length of the shear wall, but in a strap braced wall, it's very concentrated. And so you've got to be able to drag that shear force out into whatever anchorage you've got. And that could include, splices in the base track, maybe a stronger base track than normal. And of course, making sure you've got adequate anchorage of that to resist the shear. And also you want to make sure that if you are using straps on just one side of the wall, that you consider the effect of that one-sided force on moments in the cord studs. And the deflection of strap braced walls is determined by principles of mechanics, but specifically you've got to include strap elongation, compression cord shortening, displacements due to hold down and anchorage deformations. And if you're going to use screw connections, you got to consider screw slip. So, deformations of the fasteners at the end of the straps. And special bolted moment frames are a very particular type of seismic force resisting systems with really strict requirements on their usage. They are probably most commonly used for mezzanine or platform type structures inside other structures, but they can be used in other applications. And the nominal strength of the frame is calculated based on AISI S400 in terms of the member properties and the strength of the connections. And the designated energy dissipating mechanism in a special bolted moment frame is the bolted beam to column connection. So if you're familiar with these, or if you happen to get a good look at my last slide, these are made from tube steel columns with cold form joists on each side that are bolted through. And it is that bolted connection that provides the energy dissipating mechanism. And the expected strength then is based on the combination of column shear corresponding to the slip strength of the bolt group and the connection bearing strength. So you've got VE, the expected strength is based on those two terms, VS and the VB. So there's a number of system requirements for special bolted moment frames imposed in S400. And these are all based on the range of tested systems. So this is a system that when it underwent extensive testing, and because of that, it's the parameters for which you can design a special bolted moment frame are all boxed in by those test limits. So for example, there is a story and height limit of 1 story and a maximum 35 feet tall. All of the columns in the system have to be part of the special bolted moment frame. Columns have to be designed and constructed as pin-based. Beam and column sizes are the same throughout, so every beam, every column, identical. And the moment connections are the same throughout, so it's just uniform all the way across the entirety of the frame. And of course, you got to take a good look at the P delta effects when you're designing the columns in particular. So speaking of P delta, now is probably a good time to dig into that a little bit. S415, even with the 2016 supplement, referred back to AISI S100-12. And AISI S100-12 utilized a single moment magnification term alpha to account for increased moments due to member deformations. S420 references AISI S100-16, which incorporates system stability requirements that are actually more reminiscent of like an AISCE type analysis. So providing for system stability can be achieved with a rigorous second order analysis, including the stiffness reductions, or by using an amplified first order elastic analysis, or the old B1, B2 analysis to account for P little delta and P big delta moments. If you haven't been through one of those analyses, P little delta is, think of that as moments generated from deformations of, say, a column that is bent a little bit. So it's based on the deflections of the member itself. And then there's P big delta moments, which are based on lateral translation of the structure due to, in our case, seismic forces. So the B1, B2 analysis can be particularly interesting in our situation for single-sided strap-braced wall, where the strap tension generates strong axis moments. So it creates that bending that would require B1 amplification. But it is also, the strap tension is resulting from lateral translation of the structure. So it also is subject to the B2 magnification. And also weak axis chord moments, like we talked about for narrow strap braced walls, result from lateral translation of the structure. So any of these weak axis moments, of course, would need to use the B2 amplification. And another interesting point about the this amplified first order elastic analysis to keep in mind is this is not just for design of the chord studs, for example. These are real effects in the system. So if your amplified first order analysis or your rigorous second order analysis determined that your uplift forces at your hold downs were elevated by a certain amount, for example, you need to design for those forces because they are real. They're not just a means to over design something to make it kind of work. They're actually forces that are anticipated in the structure and need to be addressed. So diaphragms collect and distribute inertial forces to the seismic force resisting systems. Diaphragm membranes and cords, incidentally, are not capacity protected. In other words, you don't need to design those for expected strength or overstrength level forces. Collectors, however, are required to be capacity protected. So they do need to be designed for the expected strength of the seismic force resisting system or, omega naught level forces. Interestingly too, in S400-20, we've added special seismic detailing requirements for steel deck diaphragms. So if your design by the applicable building code requires those special seismic detailing requirements, we do now have those provisions available in S400-20. The nominal strength for wood structural panel diaphragms are tabulated in S400 for a variety of panel types, fastener spacings, and for both blocked and unblocked conditions, where AISI S400-20 can provide methods for designing the profiled metal deck diaphragms. And again, what you're going to get from S400-20 is the strength and stiffness of the membrane portion of the diaphragm. The cords and collectors and stuff you'd still need to design based on other modeling or basic mechanics. And of course, other diaphragms can be used. AISI S400 does not limit you to these particular diaphragms, the profiled metal or the wood structural panels. So you can use other types of diaphragms like proprietary systems based on manufacturers' published data or based on principles of mechanics if you've got the information you need to perform the analysis. And diaphragm stiffness, like rigid versus flexible versus semi-rigid, can determine how the forces are distributed to the seismic force resisting system. However, ASCE 7 allows untopped diaphragms with light frame construction to be idealized as flexible, regardless of how stiff the diaphragm would be by calculation. And that idealization can simplify the design, and it does have a history of working well. Now, it may not be perfectly realistic for some scenarios, but it does seem to get the job done. We'll talk a little bit more about that later on when we touch on the research done for Cfs NIST. But the equations for estimating wood structural panel diaphragm stiffness are included in the S400 commentary. So collectors are critical elements in the seismic load path and are required in S400 to be capacity protected. So collectors, of course, are the part of the system that are gathering the seismic force and carrying it to your strap brace wall or your shear wall, for example. That's why they need to be capacity protected, because they're not part of the body of the diaphragm like the membrane or the cords. They are a direct line from seismic force to seismic resistance. So capacity protection is very important. Interestingly, ASCE 710 included an exception to the requirement for capacity protection of collectors in buildings framed entirely with light frame shear walls. However, S400 did not allow that exception, and the requirements of S400 would take precedence. In ASCE 716, those two standards were synced up. So the exception now in ASCE 716 is limited to structures braced by light frame wood shear walls. So if you've got a CFS seismic force resisting system, it's very clear now in all the documents that you do not get to take advantage of that exception, and that you do in fact have to design your collectors for expected strength or overstrength. And that leads us to the second batch of questions.
We've got a lot of questions coming in here, Rob.
All right, well, it looks like we got a little bit of time yet, so.
Yeah. So I think probably the most commonly asked question was just to get some recommendations from you on software for use in analysis and design of CAFS systems.
So I guess first a disclaimer, I do some consulting work in that realm, and I happen to work on CFS Designer software. CFS Designer does include modules to do LFRS strap brace design and LFRS shear wall design. There are other systems out there that do similar types of design. I believe the Steel Smart system by the Steel Network has some nice features. I can't say that I'm an expert on the full range of software packages available. I do know that full system modeling, so where you would like design, develop an entire building model with cold form steel shear walls and stuff, are frankly not that well developed right now. Most of the manufacturers of the full building modeling software have not yet incorporated the data, and partly because the data isn't, a lot of it is kind of new in terms of the amount of information you would need to program those things. So now some of those platforms do offer shear wall modeling, but it would be incumbent upon the user to input, for example, the shear wall stiffness and so forth. There are very robust packages available to do modeling that are used a lot in academia, but to my knowledge are not as common in engineering practice. So the tools, there are tools out there that can do full building modeling and design, but in common engineering practice, there's not a lot that will do the full system. Like I mentioned, a couple of the CFS specific programs are very good at looking at elements of the system, for example, a stack of shear walls or a stack of strap braced walls. But in terms of putting it all together for the building, software is actually still a little bit light.
Does sheet steel include the use of corrugated siding?
Easy question, complicated answer. So S400 does not specifically include provisions for profiled shear walls. That said, S310 does have provisions to calculate the strength and stiffness of that system. And so an engineer could, by using rational analysis and some judgment with regard to the appropriate values of R and CD and omega naught, use that system. And of course that system does get used. It's usually in fairly lightweight types of structures like storage structures and so forth, where seismic forces are not really all that severe. There has been some research into those types of shear walls, so corrugated sheet steel type shear walls, both here in the US and internationally. And I suspect, honestly, that in our next edition of S400, those systems probably will be directly incorporated. But right now, it would require the engineer to kind of step out on their own a little bit and make some judgments about how exactly to proceed.
What are the conditions where gypsum board can be used for shear walls? And then the person went on to say that assumed design conditions are not necessarily found on construction sites. For example, there's the potential for extreme humidity and transportation damage hazard.
Yeah, so in terms of what the specific limitations are, I would say let's answer that one in the written responses, because I would want to refer specifically to S400 to make sure I don't miss something. But yeah, that's absolutely right, that gypsum board is highly sensitive to humidity, and it can be subject to damage. I think there's a number of things you have to think about if you're contemplating using gypsum board as, you know, part of your primary lateral force resisting system or seismic force resisting system. Damage is one of them. You know, for example, somebody decides to do a remodel and pulls the gypsum board off, you know, you've kind of lost your lateral system. Also, in the event of water damage, and water damage can be from a number of sources, right? It could be from a flood or a leak in your plumbing system, or it could be because there's a fire, right? So there's a fire, and the firemen come in with their hoses and start squirting down your shear walls. So yeah, there are some specific limitations, but in addition to those limitations, I think a lot of practical consideration needs to be made with regard to when a gypsum shear wall would be appropriate.
Can we use the same R and omega factor for CFS on podium slabs?
Yeah, that's another simple question with a complicated answer. I believe that you can. There's been some changes in the codes, and I am not necessarily an expert on exactly where in ASCE 7 those mixed systems are addressed. It's my understanding that there are provisions that say podium type structures can be designed where basically once you get above the podium, you pretend that the entire structure was always cold form steel when you choose your R, your CD, and your omega knot. Also, of course, if you were going to do a full building model, you know, like a full dynamic model, all of that would be borne out in the model itself, and so you may be able to avoid some of those issues. But it is my understanding that, yeah, you can do that, but I would defer to ASCE 7 for the specific limitations.
Okay, how about the last one for this question and answer session? What do you think about CFS supporting precast planks?
So I'm assuming that we're talking about a like precast plank diaphragm type system. And I have seen those systems done before. I have never designed one, so I can't speak with direct experience, and I've also never seen one tested. I would say that any type of plank system, you know, if properly designed, you know, for the right strength and all the connection systems, I'm sure can work just fine. There are considerations that would have to be made with regard to how the planks interconnect for continuity. You know, I've talked a lot today about, you know, for example, collectors and elements in the seismic load path. So concrete planks, of course, are heavy, so they're generating a lot of seismic force, but they're also, you know, the interconnection between those and whatever collector type system you're using is going to be super critical. So yeah, I would say that, you know, they could certainly be useful, but I think you'd want to really scratch your head to make sure that you've established continuity and that all of the parts of that system are going to work together as intended because of the elevated seismic mass and the lack of inherent continuity, right? Like a poured in place slab or a concrete over metal deck, for example, has a lot of inherent continuity, whereas a panelized type system or a plank type system may not. And so you may have to establish that continuity separately.
Okay, that's all the time we have, I think, for this session, and we've got one more in a little bit.
All right, very good. Thanks, everybody. So, talking about CFS construction, most CFS construction uses repetitive framing members, typically spaced 16 or 24 inches on center. Now, there is work going on at AISI and around to try to implement wider spacings and understand how those systems would work and develop seismic force resisting systems that are not tied down to those. But most common construction today does use repetitive framing type systems. Common methods include platform framing, where floor and roof assemblies are stacked on wall assemblies. There's also balloon framing, where walls bypass continuously floors and roofs. So you might have, say, a 2-story building, but the studs are just one individual stud, maybe 20, 25 feet tall, for example. And then there's ledger framing, which is almost a hybrid of the two, where the floor and roof framing is supported from a ledger on the side of the wall. Those ledger members are normally tracks, and they just attach to the inside face of the studs, but the studs only span one floor at a time. And of course, framing can be panelized or framed in place, and panelizing does offer efficiencies for repetitive subassemblies, as well as some potential quality control advantages. However, panelizing does require considerable pre-construction time to design the panels, and in addition, interfaces with other constructions, for example, concrete foundations, can be challenging due to construction tolerances in these other materials. So CFS and wood framing have a lot of things in common, particularly the use of repetitive framing and the common use of shear walls for lateral force resistance. CFS does have some advantages, including dimensional consistency, so you won't get any shrinkage, warping, or out of straightness. Steel is non-combustible, and engineers can choose members with a variety of thicknesses, flange sizes, and mechanical properties to suit their specific needs. Now, that said, CFS framing is challenged in some regards by its relative youth, and there's fewer standard construction details, and that can lead to steeper learning curves for plan reviewers and inspectors, and also, frankly, for builders if they're not accustomed to dealing with the niceties of building with steel. And of course, for both systems, wood or steel, sound and fire ratings can influence the structural details, and all of those things have to be properly coordinated. So subsystem modeling. And there has been quite a bit of work completed on small-scale fastener tests to determine the strength, the stiffness, and the hysteretic behavior of the system. So, for example, on the upper right-hand part of the slide there, you see a picture of sheet steel attached to plywood, and there have been lots of tests where they do exactly that, and then they push and they pull and they push and they pull, and they record all the deformations and forces to get the hysteretic behavior. And so the results of those tests can be used to simulate full systems, such as a shear wall. So you could take those test data and you could run those through some sophisticated analysis to determine the behavior of an entire shear wall. And that method does provide the ability to design shear walls with sheathing and fastener combinations not currently published. So if you go to S400 and you look in the tables, you're kind of bound by certain combinations of panel products, fastener spacing, steel thickness, and so forth. And with this type of system, you could go out of those bounds, right? You could venture out into new territory. And it may help us move towards full system modeling, where the seismic force resisting system and non-seismic force resisting system behavior can all be included in one robust building model, so we can understand the behavior of the entire building and not just look at it as individual parts that seem in our analysis to be unrelated, but in fact are integrally related into how the whole system performs in a seismic event. Now, AISI S400-20 in the commentary does specifically enable this method. So it does give references to published papers on the method that would describe how you could implement the hysteretic behavior of those fasteners and the properties of the panels and framing to actually determine the behavior, strength, and stiffness behavior of a shear wall type system. So CFS NIST was a study initiated in 2010 to look at the full system performance of a CFS frame 2-story structure. And both full-scale and small-scale testing and modeling was done so that we could better understand the behavior of everything from individual fasteners to the interaction of all the parts that were going into CFS building construction. So full-scale testing included multiple phases. And in phase 1, the building was shake table tested with just the design structural system. So like on the picture on the left, you can see the framing is there, and there's just some OSB shear walls along the length of the walls and in a few of the corners. So phase 2, oh, and incidentally, so we took that thing, and that blue structure that is sitting on is a hydraulically actuated seismic shake table. So we ran a variety of seismic spectra through those hydraulics to accelerate that structure, mimicking some of the North Ridge shaking, I believe it was, and measured all kinds of stuff about how the system performed. Then we deconstructed that system and rebuilt it, tested it to make sure it was the same. So we ran what was called white noise tests to make sure it was behaving the same as the original phase 1 structure. And then we started adding stuff to the building and doing additional tests. So the additional tests were completed after addition, for example, of full exterior OSB, interior gypsum board on perimeter walls, interior partitions, and finally everything through the exterior finishes, which is kind of what you see on the picture on the right. And it's worth noting also that that NIST technical note that I mentioned earlier that compared designs with ASCE 41 and ASCE 7, those were based on this building. So this is the archetype that was run through those two designs. And as expected, the stiffness of this structure increased significantly as components were added. So if you start over on the left, you'll see that the period is relatively long. And as we add exterior sheathing, perimeter gypsum, interior walls, and exterior finish products, the period goes down and down. In other words, the stiffness of the structure keeps going up and up. One of the most interesting takeaways from the testing, though, was that the structure didn't perform at all how our simplistic engineering models predicted. So the shear walls were not significantly worked even at the highest accelerations. The non-structural elements added so much to both the strength and stiffness that it kind of threw our prediction models out the window a little bit. But while our predictions were not at all realistic, the overall performance of the structure was quite good. So even the strongest shaking, which was actually, I believe it came up to either 1.1 or 1.2 of the maximum shaking that was experienced in the spectra that we used from Northridge, it only produced minor cosmetic damage in the sheathing around some of the openings. So we kind of looked at that as good news and bad news. The good news is, behavior-wise, it really did well. I mean, it performed way better than I think any of the testers even expected it to. The bad news was that, you know, these methods that we use were not doing a good job of predicting actual behavior. So quality control, QC and QA. AISI S400 refers back actually to S240 Chapter D for QA/QC. And S240 includes basic observations of installation to meet approved construction documents. Items requiring verification include shear wall and diaphragm sheathing for diagonal strap bracing. So you're going to check to make sure that what is specified is what's installed. Welder qualifications and weld fit up if there are any welded connections. Mechanical fastener selection and installation. Connecting elements such as hold downs and anchors. And screw connections. And in screw connections, we need to verify that the joints have a tight fit and that stripped or over-driven screws are limited to what's in S240. So depending on the type of connection you're making, the type of system, you can actually have some stripped screws and that can be acceptable, but they are limited. You can't have like all of them be that way. And the specifics of that are defined in S240 Chapter D. Additional QC/QA considerations include that we check that the strap bracing is installed and remains tight. So strap bracing can be difficult to install to get it tight the first time, and it can loosen as gravity loads cause shortening in the walls. And I have seen this, and I have talked to other engineers who have seen this, where on a multi-story structure, for example, the lower level strap braces got installed nice and tight, and by the time all of the upper levels were put on, the straps were a little bit loose, just because the walls had shortened slightly, allowing some loosening of those straps. So you want to make sure that before everything is covered up, that those straps are tight and properly installed. Bridging and bracing should be installed in accordance with the design documents, and the brace forces have to have a path to ground. So if, for example, you are putting CRC, cold rolled channel, through punch outs in the wall, and that CRC just terminates somewhere along the line and doesn't have any anchorage to anything else, it may provide torsional restraint to the studs, but it's not going to provide weak axis buckling restraint. As you can imagine, all the studs could buckle simultaneously in the same direction, and the cold rolled channel would just go along for the ride. So if you're relying on the bridging and bracing to provide weak axis buckling restraint, you've got to make sure that you can do that. And AISI S400 actually does have provisions to estimate the forces in that bridging so that you could properly anchor it. And the stud to track gap is limited to 1/8 inch in S240-20 for 54 and thinner thicknesses, 54 mils and thinner. And for heavier framing, the designer needs to specify the gap. And that is all of the technical parts of our presentation. Just like to acknowledge ATC, NIST, and NEHRP. Tom Castle and Ben Schaefer, who were the co-authors of TB12, Jeff Ellis, Xiaoming Wang, and Megan Halligan, who were the reviewers for TB12. We also got a lot of help from the American Iron and Steel Institute, as well as Don Allen and Dr. Roger LeBoux. Which brings us to our last question slide.
Okay, looks like we've got maybe about 5 minutes or so, 5-6 minutes to answer a few more questions.
Okay.
So just as a reminder, if you have any questions now that you haven't submitted, please type them in the questions pod. First one up, for strapping in a CFS seismic force resisting system, do you recommend that the strapping be pre-tensioned?
Yes. Yeah, that was part of what I was just talking about in the QA/QC stuff. And I've seen a variety of ways to do it. Some very complex and some very simple. But at the end of the day, you do want them to be slightly pre-tensioned. You don't want to pre-tension to 10,000 pounds, of course, and precipitate an early failure in the system. But looseness in the straps can be a really bad thing, of course, because an earthquake, for example, would kind of get a run at your cords. For example, you'd have impact type loading rather than direct loading that could yield to energy dissipation.
Do you have a feel for how cantilevered CFS columns behave in seismic events, say solar canopies or carports? And are there design considerations or concerns if the columns are offset from the diaphragm's center of mass?
So I have not designed a cold form steel cantilever column system for seismic forces. I mean, I would say that the primary considerations would be to accurately determine the force distribution in the columns, particularly if the center of mass is offset. And that may require a building model that's relatively robust that can pick all of that up. And that is one type of lateral system where a lot of commercially available and common software and engineering offices could handle that, right? You could model fixed base columns with a rigid or semi-rigid diaphragm and run seismic forces in a number of directions through it to determine, what the force levels would be. I would pay particular attention to system stability, right? So either a rigorous second order analysis or very detailed B1, B2 analysis of those columns to make sure that you don't end up with secondary moments that become unmanageable and lead to system instability. And then of course the connections down at the bottom, it's difficult to get a true rigid connection in a cold form steel, like base plate type scenario. You might, with a heavy welded system or with welds with stiffener plates, or for example, if maybe you were encased in concrete, so like a pole barn type construction, you might be able to do that.
I've previously used AISI S213 for lateral design of cold form steel. Has this become AISI S400?
So S213 was kind of divided up, so to speak. So the wind and low seismic portions of S213 are now in S240, and all of the seismic provisions of S213 are now in S400. So I would definitely say for modern designs, I would wrap S213 in cellophane and put it someplace nice where you can look at it, but don't read it again. It's out of date, of course, and has been superseded by S240-20 and S400-20.
Is there a chart or guide to help understand what V finish is to calculate omega E?
Yeah, so in S400, in the commentary, there is some information about how to determine V finish for a variety of systems, including gypsum board, plaster, and EIFS, and I believe like wood panel siding. So yeah, there is some information in there. It is a little bit limited, but there is some stuff in there. If you can't find it, of course, you do always have the overstrength fallback, right? If you're not comfortable that you're predicting expected strength accurately, you can always fall back to overstrength. But there are methods in there for common systems that can be used to give you a pretty good estimate of omega E.
Okay, I think this is the last question we have time for. Why are hold downs excluded from the energy dissipating components and the need to look at them as capacity-based components? Why is it different than wood frame shear walls?
Well, I can't really speak to wood frame shear walls and why they might consider them to be part of the energy dissipation. The reason that in cold form steel they are not considered part of the energy dissipating mechanism is primarily, kind of based on how things are tested, but also as I described earlier, the energy dissipating mechanisms in cold form systems are either in the shear panels and those fasteners or in yielding of the straps, right? So our energy dissipating systems are coming from this kind of broader part of the seismic force resisting system, whereas the hold down is a very critical anchorage portion of that. So if your hold down fails, you've got a problem, right? In other words, if your hold down fails prematurely, you are not going to be able to activate the energy dissipating mechanism of your shear wall or strap braced wall. That's why it's capacity protected. If somebody asks, gee, is it possible to maybe develop or design a hold down that could dissipate energy? I'd say sure. Yeah, there's probably ways to do that, right? You could design some sort of a yielding mechanism in a hold down that could work. But you want to be super careful, right? Because you absolutely positively do not want that hold down to disengage, right? I mean, that is a critical part that's resisting overturning forces. So you'd want to tread very cautiously on any path that led you towards using that to dissipate energy.
Thanks, Rob. If you could just forward ahead one slide, and just as a reminder to everybody that we will provide written responses to all the questions that we didn't have time to get to today. On behalf of the Applied Technology Council, I'd like to thank Rob for his presentation, and thank you to everyone for joining us today. For those who registered today, expect to receive a follow-up email with a link to the recording of the webinar and a participant feedback link. Please provide your feedback because we use this information to continuously improve our webinar program. For those who attended the webinar and paid for a PDH certificate, expect to receive an email with that certificate within 2 weeks. If you registered for this webinar, attended the full webinar, but have not paid for a PDH certificate and would like one, use the link provided in the email following the webinar to order a PDH certificate by the end of the day. Lastly, before closing, I would like to just briefly mention that ATC provides trainings for organizations on a variety of technical topics like ATC 20 and FEMA P154. Due to the COVID-19 pandemic, these courses are currently being provided through remote instruction. If you're interested in learning more, please visit the ATC website. This concludes the webinar on seismic design of cold form steel lateral load resisting systems, brought to you by the Applied Technology Council. Have a great day.